Let's see Gattermann-Koch reaction. Benzene is converted into benzaldehyde in the presence of carbon monoxide, HCl and AlCl₃. This is called EAS reaction, electrophilic aromatic substitution reaction, in which an electrophile, this CHO, formyl carbocation in our case, is going to added. At the same time hydrogen H plus is going to eliminate it. So this reaction is going to do addition as well as elimination, and this reaction called a substitution reaction. And this addition and elimination take place on the aromatic ring, so we called it electrophilic aromatic substitution reaction. In our case we are going to eliminate hydrogen from this side, and we are going to add aldehyde at the same side, so H is gone and aldehyde is added. Now let's see the mechanism. In the first step, carbon from carbon monoxide is going to abstract a proton from HCl and will form CHO. This is a formyl. Now the interesting thing is that this oxygen is more electronegative, so it can have that pi bond in the form of a lone pair and will be stable with two valency. At the same time, this carbon will be a positive carbocation, electron deficient, so this is now become an electrophile. And the first step in which we are going to generate this CHO electrophile, and further we are going to add this on our aromatic ring and will kick off proton. Now what this AlCl₃ is going to do, this AlCl₃ is going to act as a catalyst. It's a Lewis acid and electron deficient species. When this carbon is going to get that proton, this Cl will have this bonds electron and will form a chloride. And now this chloride is going with this AlCl₃ and will form AlCl₄. What this AlCl₃ is going to do, it will have that chlorine, and that proton, that hydrogen from HCl is going to be free, so that carbon can easily get that proton and can form this electrophile. So it is going to increase the rate of reaction as well. Now in the next step, this aromatic ring is going to attack on this electrophilic carbon. How this aromatic ring is going to act as a nucleophile? That is in presence of pi bond, and the pi bond is formed by sp2 carbon, and that p orbital is having a poor overlapping, and because of that, that electron density is more reactive. It's quite free, so it can react, and that electron density is this ring is going to use to attack. One of the carbon from this is going to use that and will attack and will make a new bond, and this bond is going outside from the ring and will have a new bond with this carbon. Now check it. It is our aldehyde. This is our addition of that CHO, that addition step. But at the same time, the next carbon, neighbor carbon, is being carbocation because of disturbed valency. That bond is now no more. It is now shifted outside to form a new bond with this CHO. Now ring is going to lose its aromaticity, and to restore that aromaticity, this ring needs to eliminate proton from this side, eliminate hydrogen from this side. Now how this hydrogen is going to kick it off? Now how this hydrogen is going to eliminate? For that, AlCl₄ is there, in which AlCl₃ and that Cl is that. Now that Cl is going to abstract that H and will form HCl. So HCl and AlCl₃ are going to recover after completion of the reaction. H is gone, and now this bond is simply shift inside the ring, and will form a double bond again and will restore the aromaticity of ring, and this is our benzaldehyde.